Good evening, ladies and gentlemen. Welcome to Lecture 8 of Topic 2 of Unit 4, Photons. This video will be going through the main ideas of Chapter 11.4 of Book 2. Please complete this reading before class. Here are your learning intention and success criteria for the chapter. Please pause the video and attempt to complete the KS table. Alright, so we can see here the learning intention for this video is that you can describe photons and you can calculate the energy in a photon in both joules and electron volts. So we need to be able to describe it, we need to be able to calculate the energy, and then we need to convert joules over to electron volts. So we need to know, well, what is a photon? If we don't know what it is, we can't describe it. We need to know what an electron volt is, because that's something slightly new for the Year 11s listening. In terms of skills, can you calculate the energy in a photon? And finally, can you convert between the two joules to electron volts? So, why do objects give off light? Now, in our last video, we discussed that objects, as they have more heat, energy give off more light. What's heat? Now, if we go back to Unit 3, Topic 1 at the start of this year, heat is the vibration of atoms. Now let's think about atoms for a second. As we can see here in our image, atoms have charged components. So they have a moving or an electric field when they vibrate, because if we have a moving negative charge, then it will give off an electric field when it moves. Same with the positives. Okay, so a moving charge equals a changing electric field. And as we talked about in Unit 4, Topic 1, a changing electric field creates a magnetic field, and then vice versa, and that is called light. So let's have a look at that. So it moves, it emits a field. Moves back, it emits a field. And we'll just keep doing that over and over and over again. So, photons. Now, Planck, with his study of black body radiation, reasoned that the vibration had to have some multiple of the smallest amount of energy. He called that quanta. Okay, so each frequency has some quanta, or some multiple of quanta. And the light quanta, the smallest multiple, was called a photon. Okay, so think of a photon as the tiniest packet of light. However, it only comes in certain sizes. Think of it like in our currency, the smallest note is $5. So if you have a bunch of notes, it will always be some multiple of $5. So it's a bit off kilter there today. So, Planck's equation. Planck derived a formula for determining the energy of each quanta of light at a given frequency. The formula is E equals HF. Now, E is the energy of the light wave. This is only for light waves, not sound waves, by the way, just light waves. Measured in joules, Planck's constant provided in the formula booklet, and then we have the frequency of light there in hertz. Apologies, I don't like to do this live, but everything's been a bit wonky tonight. Now, we have to talk about electron volts, because all the way back in Unit 2, we mentioned electron volts when we were looking at nuclear decay. Often light is represented in electron volts as the energy levels for each photon are quite low. So the conversion for joules to electron volts is given here. Okay, to turn joules into electron volts, we need to divide by 1.6 times 10 to the negative 19, and to turn the other way, we need to multiply. Now, the number is provided in the formula booklet under our constants for electrical circuits. Here's our 1.60 times 10 to the negative 19 joules. Think of it electron volts, electrovolts. It's dealing with the charge on an electron. Okay. You'll have to remember which way to convert. I always think of it like, well, if my joules is very small, I want to get a number that's not so small. And so if I divide by a really tiny number, I'm going to end up with a bigger number. Okay, because the goal of electron volts is to make the numbers a bit bigger and easier to deal with. Because remember, this thing was sort of really developed when we didn't have computers so much, and all this math was done by hand. So finally, just to keep in mind though, in all the formula that we've seen where there's energy, you must be working in joules. So let's have a look at an example. calculate the energy in joules and electron volts of a quantum, a photon, of violet electromagnetic radiation, just a fancy way of saying violet light, of wavelength 450 nanometers. Give your answer to 3 sig figs. Okay. Make sure that light's okay. Yep. Alright, so we are dealing with violet light, and we're told that the wavelength is 450 nanometers. Remember, we need to convert that. 450 times 10 to the negative 9 meters. Just as a recall, like all these metric prefixes, they are actually in your formula booklet as well. So don't forget that. And we're told we're dealing with light. So c is the velocity of light, is 3 times 10 to the 8 meters per second. Now, a couple of ways you can do it. You can substitute the wave formula into Planck's equation and then get your answer, or you can work out the frequency and then work out the energy. One thing I like to keep in mind, or that you really should keep in mind, is that if you have some energy, okay, that's directly proportional to frequency just through a constant. So really, energy and frequency is almost, they're just two sides of the same coin. And because we're dealing with light, it will be proportional as well to wavelength, or should be really, I should say it's inversely proportional to, 1 over wavelength. That's probably the wrong symbol to use here, but what I'm trying to get you to think is that if you're told any sort of wavelength, you have frequency and you have energy straight away whenever you're dealing with light. If you have frequency, you have energy and wavelength. If you have energy, you have frequency and wavelength, because they are only one-step formulas to convert, and they only need a constant. So because if we look at these formulas, technically for waves, V equals F lambda, or if we're dealing with just light. So here we have C, which is a constant. So if I have this, I must have this, and vice versa. If I have wavelength, I must have frequency. Okay, and then if we look at our energy, E equals HF. H is a constant. So if I have F, I have E. And if I have F, I have lambda. So these things all connect together. Okay, it's important just to keep that in mind as you are doing these, especially whenever you're reading questions. So if a question tells you, oh, it's just got some color, well, the color, you know the wavelength, and from the wavelength, you know the energy. Okay, let's do some substitutions. I'm going to rearrange. Let's see, I need F equals C over lambda equals 3 times 10 to the 8 divided by 450 times 10 to the negative 9. And my calculator. 3 times 10 to the 8 divided by 450 to the negative 9. So it'll be 6.667 times 10 to the 14 hertz. How are we doing? Good. So now we can take that, substitute into our energy equation. 6.626 times 10 to the negative 34 times 6.667 times 10 to the 14 times 6.626 negative 34, and we're going to get an energy of joules of 4.4. What was this? 3 sig figures? 4.42 joules. Though molding hasn't properly rounded for the joules value. Okay, so 4.42 joules times 10 to the 4.42 times 10 to the negative 19 joules. Pretty small number. Okay, now we want to also convert this into electron volts. So we need to divide by 1.60 times 10 to the negative 19. So you can see here the 10 to the negative 19 divided by 10 to the negative 19 is going to cancel those off. And so we're just going to be left with a whole 4.42 divided by 1.6. And we're going to end up with something a little bit over 2 there, which means that we're dealing with whole numbers, which are a little bit easier. I'm going to show you just the units for this conversion. It's just electron volts per joules. And so the joules cancel and you're left with electron volts. So that would equal about 2.8 electron volts according to thing, even though the question did ask for 3 sig fig, so he hasn't used 3 on either of those answers, but that's okay. So pretty straightforward sort of question. You may find that you would like to prefer go E equals HF equals H C over lambda, and then just substitute it all in. That is perfectly fine as well. You would get the right answer with that method as well. Okay. Okay, so pretty brief one. In this video today we've looked at the following. We've described a photon as a packet of light. We've calculated the energy of a photon from frequency and wavelengths, and we've converted joules to electron volts. Okay, it's 3 straightforward processes. For your entrance to class, please complete questions 1 to 9 in chapter 11.4 and copy your answers into the 4.2.8 space on eLearn. Thank you very much. Have a good night. Bye.